I guess when you discover a completely new elementary particle, everyone notices. Thank you very much for noticing. This evening, the SLAC Public Lecture Series is proud to present a lecture on the newly discovered Higgs Boson. The lecturer will be Emanuel Strauss. Emanuel is a SLAC staff member who's sometimes here, but more often stationed in Geneva, looking at this huge data stream that he will describe from the ATLAS experiment at the Large Hadron Collider. The data passes through his hands and out to a huge collaboration of people who, as you folks undoubtedly heard on July 4th, scored a great success. Emanuel is now a postdoctoral fellow here at SLAC. He's a graduate of the State University of New York at Stony Brook. He has a lot of experience in particle physics, and I hope he'll transfer some of that to you this evening. So without further ado, thank you very much. We'll hear about what it looks like in the shadow of the Higgs boson.
Okay. So, is this thing on? This is working? Okay. There are a lot of you. You guys know this is a physics lecture, right? Okay.
I'm sorry, I was also supposed to tell you the drill. Please note the exits in back and in front in case there's an earthquake or some other catastrophe. Okay, now that's the end of the hour.
All right. So, in the shadow of the Higgs. Well, it's been alluded to. I guess everyone here probably knows. I assume that's why you're here. There was some pretty big news on July 4th. Made the papers and everything, yeah? Katie Holmes and Tom Cruise broke up, which I'm sure you're all heartbroken about. Also, something else. And I think it fills me with a fair amount of joy that this got a lot more time in the newspapers than the other. At the LHC, ATLAS and CMS, the two biggest particle detectors on the ring, announced the observation of the Higgs boson. This is, it's difficult to express just how important this is. It's a historical event. But maybe it's not always clear to everyone else why it's so historical. So I'd like to try to convey to all of you a little bit more about what this is all really about, why it's so important, how we got there, and maybe a little bit more about what's next. So the Higgs in a nutshell. For those of you who might have something cooking, need to get out of here quickly, this is it, and then after that you can go. Right? We have this thing we call the Standard Model. And this is a framework which describes our understanding of the workings of the visible universe, all of its particles, all of its forces. And it does an admirable job of making predictions that we can test and get positive results out of. We can make mathematical calculations that predict values that we then measure and get right to parts per billion. It's amazingly precise. But there are things that are not quite right. Namely, there was this problem where it didn't account for the mass of fundamental particles, so things like the electron. And that's upsetting for something that works so well otherwise. And in 1964, Peter Higgs and a cadre of other physicists proposed this mechanism through which all other fundamental particles are imbued with mass. 1964. Almost 4 decades later, LHC announces the discovery of the Higgs particle. So the process of getting there is a long one. So I'm going to take a little bit of a detour to try to give you all of the tools that I think you need to really get what's going on here. Physics has this long history of attempting to understand the laws of nature, right? And that's sort of what it's about. And we do this through the scientific method. We construct theories. We make predictions with those theories. We then test those theories. We see how well the theories worked. And then we revise if we have to. In particle physics, the experimental apparatus that we have for testing those theories are particle colliders, where we accelerate particles close to the speed of light. We give them a whole ton of energy, and then we smash them together to see what comes out. And what comes out is, you probably know by now, E equals mc squared. I'm sure you've all heard of Einstein's famous equation. Through this, we can reach new matter and study it. And that's what it's all about. It's taken us through a whole series of steps in which we have refined our understanding of nature. If you kind of look around you at everything that's there, this table, your desk, whatever, you might look at stuff and, okay, well, got something in my hand, in this case, a sugar cube, matter. It's made of stuff. And as our ability to look at smaller and smaller things got better, we came to the understanding that there were molecules. And this was, we unraveled a layer of reality and got a little bit closer to what we thought was the truth. And as we got further and further in, we realized that the atom itself is not so indivisible after all. It's got electrons circulating around it. And in the nucleus, we find protons and neutrons. Okay, so now we've unraveled yet another layer of this onion. And then, we dig even further and we realize that the protons and neutrons have in them quarks, which we now think are fundamental. So this is yet another layer that we've kind of unraveled. And as we stand now, we believe quarks are this fundamental thing, that there's nothing else that's smaller. We think they're basically point-like. But there are theories out there that they might be themselves representations of something else that underlies them too. So that's the kind of understanding we're trying to build. And as we try to build this understanding, we find things that need better explaining. And so the Higgs is one of these things. So as we were unraveling all of these layers, there's a structure that made itself apparent. You're all, I think, familiar with the periodic table of the elements. And in a similar way, so the periodic table of the elements allowed Mendeleev to make predictions about elements that had not yet been observed. Right? Before they were ever seen, he was able to predict their properties, and then sure enough, we found them in nature. And the reason this was possible is because there is an underlying system. Well, as we look at these quarks, as we look at electrons, as we look at all of these other fundamental particles, we realize that there's a system. And in this case, you have quarks that have 3 fundamental families, leptons, where I'm talking about electrons, muons, and taus. I'll touch on all of this again, that themselves also have 3 fundamental families. And then forces have particles which represent them as well. So we start to build this picture that's very rich, but very structured. Getting there really took, it took decades. This was no piece of cake. Over the course of about 70 years, we went from understanding in 1899 that atoms had these electrons forming this cloud of charge around them, right? To understanding that not only that, but matter was almost completely empty. This is something that when I was learning about it in high school always kind of blew my mind, right? Is that all of the mass, all of the matter that we talk about is really packed into this tiny, dense nucleus of positive charge. So you have negative charge floating around it, positive charge on the inside. The fact that it's all positive will be an important point when I get to a later slide. Yeah. And then, another 20 years or so later, we realized that this dense piece of matter is made up of these protons and neutrons. This was hard-won knowledge. And then things changed really fundamentally. There was an experiment performed right here at SLAC, so in your own backyard, in which we came to understand that protons and neutrons themselves are composite objects. So we discovered these up and down quarks. A few short years later, we knew not just of this up and down quarks, but of 6 types of quarks total. And we discovered this through a zoo of particles that we were able to discover at particle colliders. Things like pions, kaons, japesize. You can find these things on Wikipedia. So these experiments were always about getting to smaller and smaller scales. if the atom is 10 to the minus 8 centimeters, right? 0.000000000, I think that was 8 zeros centimeters. The nucleus itself is even smaller, 4 orders of magnitude smaller. And these quarks, they're over here, less than 10 to the negative 16 centimeters. So as we go up to these higher energies, we're also going to much smaller scales. And we're studying these things, and we discover some weird things about them. The electron isn't alone. Quarks have these 3 families. The electron has 2 other siblings, right? So I think everyone here is familiar with the electron, right? It's, see light, electricity, all of these things that are happening, it drives chemistry. Well, there's this other heavier sibling called the muon, which is about 200 times heavier than the electron. And it's produced fairly abundantly in our universe. It's actually, you can detect it, the Geiger counter. You can see this even though they are fairly exotic. But you don't see it running through your electrical circuits here. And then what we discovered through all of these experiments is that there's also this thing called the tau, which is even heavier. Right? So the muon is 200 times the mass of the electron. The tau is 3,400 times the mass of the electron. It's this giant heavyweight. And that's, again, something that really isn't fully understood. And the Higgs is in large part meant to help us understand all of this. You can actually buy electrons, muons, and taus. That's what these little plush dolls are, going from the smallest to the largest at the particle zoo. I don't mean to, I'm not being it's not an endorsement. I'm not being paid by them. All right, so the electron, muon, and the tau also have a corresponding neutrino, which itself is nearly massless, tiny, tiny masses. They zoom by, they barely interact with anything, and yet they're one of the most abundant things in the universe, producing nuclear reactions, producing our sun, things like that. So there's this very rich thing going on. All right, so I've talked about, if you remember that structure graph that I showed you, I've talked about everything on the left now. We can talk about the stuff on the right. I said something that you might have found a little bit weird. I said that the forces have particles. So I'm going to talk about that a little bit now. So as it turns out, the forces that we experience are actually mediated by what we call bosons, by these particles. Boson, Higgs boson. I'm getting somewhere, all right? Okay, so we know this through experiment, we know this through theory. We have a pretty good understanding of these things. Electromagnetism, right? So magnets, all of these things, you always think of those field lines. So actually what's happening there is the exchange of information via these particles, photons. Yeah? I've always enjoyed the idea of the fact that actually forces acting on things are in some sense an exchange of information, right? If 2 magnets feel each other, there's actually one telling the other it's there, the other telling it's there. And the way they tell that to each other is through the exchange of these photons. So this extrapolates out to the other forces that we've discovered. The weak force, which I'll talk about in the next couple of slides, is mediated by W and Z bosons. The strong force is mediated by gluons. And then gravity is a tricky one. We strongly believe it's mediated by the graviton. We've given it a name. We've never seen it. There are experiments out there for it. Okay, so I'm not going to talk about gravity that much because I think everyone here is pretty familiar with what gravity is all about, right? Newton getting hit in the head with an apple, satellites using a slingshot procedure around the sun, around the Earth, things like that. I think everyone kind of has a pretty decent grasp of what happens with gravity. There's also the fact that it's not very well described at the quantum level by our standard model, which is one of those question marks I told you about. Electromagnetism, again, I don't think we need to talk too much about this. You're all familiar with magnets that pull or push against each other, and you've experienced it in all facets of your life. Here, this is the aurora borealis. So you have, stripping, you have ions produced in the atmosphere, you have, these beautiful displays made. It's a thing that we have in our daily lives. I'm going to talk about what I think is a little bit less common to all of us, what we don't really experience in our daily lives. I'm going to talk about the strong interaction. This is one of the things that we really came to understand as we were building these particle colliders and going to higher and higher energies. So I said to you that the nucleus is all of these positively charged particles as well as neutrally charged particles. And you should have possibly thought to yourself, but positive charges, they should repel. Why doesn't the nucleus just fly apart? As it turns out, there is another force which binds the proton together, which is itself 100 times stronger than electromagnetism. But it's a little quirky. So if you take two magnets that push each other apart and you bring them close together, you feel the strength of that force growing as you bring them close together, right? Bring them apart, they barely feel it anymore, right? So the strong force actually acts inversely to that. The strong force only acts on a very short scale, but within that scale, it actually grows as you increase the distance between the particles. So what happens is you have the exchange of gluons, the mediator, that keep everything stuck together in the nucleus. If you try to go too far, the force in some sense snaps. And what happens when it snaps, it actually it releases this huge amount of energy. So you think of this maybe as a spring, right? You pull a spring apart, it gets stronger and stronger. The spring snapped. Here, this spring, instead of just kind of being defunct, now has a whole bunch of other springs set up. So it's a pretty important force for what's going on in our atoms. Okay, the other one you might not be quite as familiar with is the weak interaction. This guy is responsible for radiation. And it is the reason for which we don't see these heavy particles in the wild. They'll decay typically through the weak interaction. So I told you the W and the Z are the mediators for this guy, and this one is also on a very short range, about 1/100th the size of a proton. Outside of that, we don't see it. So we don't see the strong force and the weak force in our daily lives, right? But they're very much real, and they're a very big part of the experiments that we do at the LHC. Okay, where am I going with all of this? Why this detour? Well, now I claim you're all particle physics experts. You understand all of this over here on this graph. You have an understanding of the fact that we have these quarks that we can produce in our experiments. You have an understanding that we have these electrons, muons, and taus, that we have these neutrinos. You have an understanding that forces are mediated by these particles. So where does the Higgs come in? I've told you a couple times I've told you a couple times now that the Standard Model does an excellent job at predicting things, except where it doesn't. Now, that doesn't mean we shouldn't believe it. It doesn't mean that we shouldn't have faith in the Standard Model. It means it needs refining. So if you think kind of back, to the Greeks, they had this like very general understanding of the world. They kind of came up with the idea of atoms, but they didn't really understand things very well. They thought, earth, fire, water, wind were basic elements. It's not very good. Their view of the world was not very refined. But as time rolled on, we came up with this idea of Newtonian mechanics, right? And we came to understand things pretty well. And we refine our understanding of the world. So in this totally hokey setup that I have here you exist before you have any real understanding. This is stolen from Pixar, by the way. They have a paper about how they render hair. So this is our initial understanding. And so you get to Newtonian mechanics, and now you look at this, and from above, it looks like the back of a head of hair. That's great. But those in the front row will notice that maybe it's not so great. To those in the back row, it looks pretty good, right? So as you get closer and you better understand this, you realize this is a totally good approximation of hair until you need something more. And so they add some extra layers to the rendering, and they get to this, and this looks great. So in that sense, the Standard Model is our closest approximation to reality. But we're not quite here yet, and we'd love to get to real hair. So in refining the Standard Model, it's time for a Higgs. Now, Higgs is clearly the name that you've all heard before. It turns out a lot of people came into this equation, sometimes working independently, sometimes not. It was in some sense the right time for the right idea, and it kind of sprung up in a number of different ways. It also was refined over a long period of time. But those who were kind of responsible for it that get cited the most, and this is actually a very contentious subject because there's talk of Nobels in the air now, and you might notice that there are more than 3 people listed here. Makes for some uneasy conversations sometimes. In any case, Higgs came up with this idea of of this mechanism, as did Engelert and Brut over here, and Kibble and Gralnick. And all of these things together form a much better picture that was then refined on by other people who actually did get Nobels out of it. There's a whole bunch of information that was really developed over time. And it all comes down to this. It's pretty easy. Okay, maybe not so much. So I don't want to go through that formula. I'm sure you don't want to either. It scares me. So maybe let's try to build up a more intuitive understanding of what the Higgs is really about. So I told you that they came up with a mechanism, and I'm kind of dodging an issue here, which is a subtle one, because there's a Higgs field and there's a Higgs particle. So if there's this Higgs field that permeates all of space, the way that these fundamental particles get mass is by interacting with that field. So if the field is uniform everywhere, then things have mass in a uniform way no matter where they are in the universe, right? If you're trying to kind of get a better understanding of what I mean here, this guy right here, pretty well, makes a tiny little splash. Quickly, he would be a pretty light particle. This fellow over here, his form is maybe not quite so good. I think he'll make a little bit more of a mess when he hits the water. And so he interacts with that water much more strongly. And in this analogy we're trying to build here, he would have more mass, right? So it's the movement through this field and the interactions with this field that give things mass. The bigger the splash, the bigger the mass. The Higgs boson is actually an excitation of that field. So now this is tricky stuff. I don't understand it. I kind of, a little understand it. I'll try to convey to you what I understand. So quantum mechanics teaches us that what you might think of as a continuous field is actually discrete. You don't have just these completely continuous blobs of things. You actually have constituents to fields. So I told you, that now I'm coming back to some previous slides. There's a reason I was dealing with some of these things. I told you that electromagnetism is mediated by the photon, right? It's not just these continuous field lines as you might draw them on a graph. As it turns out, you have these discrete packets of information. So one imprecise way to think of it is just as water is not continuous, right? It's made of H2O. And just as electromagnetic fields themselves are made up of photons, well, the Higgs boson is what makes up the Higgs field. It's these excitations of the field. So this is an imprecise analogy, but frankly, I haven't found any other better ones. A lot of us have been trying to figure out a good way to express this without having to go through a full course on quantum field theory. And I think maybe in the few minutes that I have, it's the best we can do. But I hope that now you have a sense that the Higgs particle that we're searching for is actually indicative of this Higgs field, and the Higgs field is what gives you the mass. Is that a little bit clearer now? Yeah? Some people are nodding, some people have their eyes glazed over. It's the best I can do, so we're just gonna go forward, hoping that I haven't lost everybody. Okay. So, why is this so fundamentally important? Well, it fixes things in a big way. The masses of these fundamental particles, so the electron, the muon, the tau, all of those quarks, right? They depend on this Higgs for their mass. And without wanting to get too metaphysical about the whole thing, without the Higgs, you would have some pretty serious consequences. The electrons would have no mass. They had no mass. They'd basically be zooming across the universe. You would not be able to ever have formed atoms, right? So you just have these ions running around, and without these electrons, you'd have a very difficult time doing any kind of chemistry. And without chemistry, you'd have a very difficult time getting us. So this very much answers the question, what are we made of? And how did we get here? So I think that this, okay, I'm in the field. Clearly, I'm one of the ones who's been converted. I think that this is fundamentally important and just a totally worthwhile thing to be searching for, right? I think this is a really cool thing to be searching for. And I think it's in some sense a very validating thing to be looking for. And so when all of this excitement is generated and all of you people show up for this talk, it feels great to have you all here. I mean, it's super to have this many people interested in our field. And I hope that you kind of get a sense of why it is that we in the core community are so excited about it as well. OK, so I've told you that the way we play is by accelerating particles up to about the speed of light. We inject a whole bunch of energy into them, and we smack them together. We've been doing this for a very long time, and every time we can get to higher energies, we can get to smaller scales, right? Remember, I told you we're always going from smaller and smaller scales. We're always zooming in more and more. Our microscope is getting stronger and stronger, yeah? So this here is a plot of some past accelerators. The LHC is all the way over here. It's the giant. If you start off around 1960 or so, we were playing in what we call the GeV range. It's a unit of energy. And every 10 years or so, we've gone up about an order of magnitude in energy. We've been moving logarithmically. I should also point out that a number of these things have been housed right here. A number of important discoveries have been done right here. You really have in your backyard some amazing physics that's been done. But let's be honest, this is where the big game is now, right? So this is the LHC. The LHC is here in the tens of thousands of GeV units. It's 7. It'll be doubled. Sorry, it's 8. It'll be doubled probably in 2 years. It is by far and away the most energetic collider that we have, and therefore it is the one that has given us the closest view of underlying reality. What does the LHC look like? Well, so here's an aerial view. The LHC is this 26.7 kilometer ring that's housed, so the French border is right around here. So it's housed on the border between Switzerland and France. I'll give you a little bit extra important information. What you have up over here, this mountain range over here is the Jura. It extends all the way out into Germany and Switzerland. Gorgeous biking and skiing. Out in this direction over here, you have Mont Blanc. My office is right over here, across the street from where the detector is underground. I bike across the French border every day here to get home. Luckily, they don't stamp your passport each time anymore. So the LHC is this series of tubes. Tubes that keep growing, built on previous accelerators, actually. So when we accelerate these protons to 99.99991% the speed of light, things don't start off that fast, and we have to do it in stages. We begin over here at what's called the booster. We accelerate bunches of protons. We're not accelerating one proton at a time. Yeah? We're actually accelerating millions of protons per bunch. They travel in bunches. And we do this in a number of stages. So after we've accelerated a couple, thousands of protons, we send them here to the proton synchrotron. They get accelerated further. They go up here to the super proton synchrotron, because it's bigger. And because you can't have a super proton synchrotron, we then have the LHC. So after they've been accelerated here in the SPS, they go shooting in opposite directions along this big ring. And you'll see here you have the two biggest detectors, CMS and ATLAS, are the ones I'm going to focus on today. But there's a lot of other physics that gets done at CERN. CERN is really this very big multi-purpose lab. There are neutron experiments, there are neutrino experiments that these neutrinos get sent all around the world, like to Italy and things like that. They race the speed of light. Along the ring, we have other detectors that focus on some other branches of physics, ELISE and LHCb. There's a lot of stuff going on, but we don't care about that today. We're just talking about the Higgs. The LHC is huge, so are the detectors that we use. So our data is collected by this giant Frankenstein. It's, as far as I know, ATLAS and CMS are the two largest scientific apparatus that we've ever built. They have multiple stages. When there are collisions that happen right here, you can see it's tiny on this scale. We have what we call a tracker, which allows us to measure charged particles like electrons and protons coming out of the collision. Around that, we have what we call a calorimeter, which is essentially just big, dumb material that we smash energy into. And it's, we can measure the energy that's deposited into these big slabs, and we can then get an idea of what's been coming through. And then we have the muon measurement device all the way out here, because muons just kind of shoot through this guy. I have here the dimensions of ATLAS. You can get a sense of scale from these guys here. When we're actually colliding protons, they are asked to step off the detector. It would be considered hazardous to their health and to the health of our detector both. CMS, our competitors and sometimes friends who are across the ring, have, so CMS stands for compact muon solenoid. CMS is compact only in comparison to ATLAS. It's huge compared to everything else. It's 21 meters long, 15 meters wide, 15 meters high. And if I look between these two pictures, you get a sense that, although this is clearly the better graphics, the structure is kind of similar, right? They do the same thing. They try to measure charged particles, electrons and protons, then they smash things into big slabs and measure the energy there, and whatever makes it through, they try to measure in this muon spectrometer. The technologies are actually very different. The philosophies that went into the design of these apparatus were really divergent, and yet somehow, and I think personally that this is actually a result of all the hard work of the people who imbue spirit into this. Despite having vastly different technologies, these two detectors have performed basically neck and neck, which is good because it'd be kind of a little weird if one saw something and one didn't. It'd be uncomfortable at cocktail parties. So the detector, so the LHC is huge, the detectors are huge, the collaborations are huge. ATLAS and CMS, ATLAS, as of I couldn't find newer numbers. So all I have here is from December 2009, where ATLAS was 2,900 scientists from 172 institutions, universities and labs. CMS is 3,000 with 155 institutions. What does the world look like to these guys? This is a plot, this is a map of all of the places that work on CMS. So you have an entry for each of these institutions. And then here you have the same thing for ATLAS with all of the countries that are part of it. I mean, we cover all but one continent. It's this giant global endeavor, which is another very cool thing about this from a personal perspective, yeah. The schematics are cool, but pictures are cooler, right? So this is while CMS was being installed. This guy was probably just asked again just to stay there for a sense of scale, because otherwise you look at this and you kind of lose a sense of how big this can possibly be. But this is when they had to lower these things in pits, and then they started assembling them like weird Lego blocks. There are some cool videos of the pieces from these detectors being brought underground, and there's what looks like centimeters of space on the sides of the walls where they could scrape these $1 million detectors. And it went admirably well. Here's a picture of ATLAS before the inner part was put in. So if you remember that plot, it had all that weird structure outside. That's this stuff, some people working inside. Every now and then they let me futz around down there. This clearly has been filled in now. Yeah, we don't take it out anymore. So you can't really get a nice picture that gives you a sense of scale of the intersection anymore. Everything's obstructed from view. The protons that zoom around the LHC, how do they do it? Well, this is a magnet structure that we use to bend the protons as they're going around the ring. This is kind of a big structure for tiny little beams. The protons, they're actually just these little black caps over here. That's the beam pipe for the protons. And even that isn't, even there, the protons don't take up the full size of that. The rest of this stuff is all, for maintaining the integrity of these magnets and our ability to, bring these protons into collisions. The beam pipes themselves are kept at 1.9 Kelvin, different temperature scale. To give you a sense of things, space is 2.7 Kelvin. The triple point of Mercury, 3 Kelvin, right? This is one of these the coldest places you'll find anywhere. It's also amazingly empty. We don't want these protons hitting anything except each other. So if there was air in here, they'd hit air molecules and they'd do all sorts of nasty things that we don't want. In fact, dangerous things for our apparatus. So we keep these things amazingly empty. We have a vacuum of 10 to the negative 9 pascals where the protons collide. Again, to give you an idea of what this abstract number means, if you're sitting at sea level, you're at 10 to the 4 pascals. If you're sitting at the moon, I would like to know how you got there, but you're at 10 to the negative 7 pascals. It's even emptier than space. This is what the ring actually looks like, once it's all put together. The protons are now now shooting around at 99.9999991% the speed of light. What that means is that they circle this 26.7 kilometer ring 11,000 times per second. And when they finally do collide, they're 100 times hotter than the sun. OK, things get complicated when they collide. I told you that this proton and these neutrons are made up of quarks. But the picture gets really messy when you're talking of really small scales. We don't have a deterministic, we can't predict where a quark is in a proton. In fact, what we have is we can only make kind of probabilistic statements about how things are going to happen. So if you have two protons that are coming together, what you care about is the quarks interacting. And as they get really close, now you have the chance of having a quark interact. But it's not like there's this well-defined circle. So I've tried to represent this for you by giving you a sense that as you get deeper into this proton, these little, I tried to make the size of these circles representative of the probability of actually finding one of them and having a collision. So what happens is when you're on the periphery of this, you will find some up and down quarks. And as you go in, the more they overlap, the more you have a chance of actually having an interaction. And then you'll notice that there are some guys that are like wrong colored here. You can find totally weird things inside a proton, things you wouldn't at all expect. And these come into our experiments. So these interactions that I'm talking about, it's not like billiard balls that come together and shoot off, right? It's more like maybe paintballs hitting each other and shooting off. And there's this detritus that just shoots everywhere. And it's this giant, messy fireball kind of a thing. The CERN PR office is great. They have this video that shows you, the protons being accelerated in the booster. And so you can follow the whole trajectory, right? Then you go to the proton synchrotron. And they come out here to the super proton synchrotron. And you can see here they're still going in the same direction. They get shot off in opposite directions. And so now we get an inside view of the LHC and of some graffiti that someone left around. And we're following the trajectory of protons now. We're zooming along the ring. Some magnets just curved us. And so here's this proton and the quarks inside of it. As the proton gets more and more energetic, the quarks have more and more energy. And it's this roiling sea of activity. And here we have the Atlas detector. Protons come in from opposite ends, and boom. So each of these lines is meant to represent a charged particle shooting off. Then you have, OK, maybe I'll wait until it stops rotating because I don't want to make people dizzy. So then what you see is that energy is deposited in these big slabs that I talked about, the calorimeters, as just these jets of particles. In fact, that's what we call them. We call them jets. Jets of particles are produced and smash into our calorimeters. So this is actually a representation of an event that we recorded with Atlas. This is exactly what you would see, maybe less in Technicolor. That's maybe a little confusing to see, but oh, yeah. Well, so if Sheldon Cooper was in the audience, he'd probably have interrupted by now to tell you all that I've played a little bit loose with some facts. There aren't fireballs in there. It's actually a really messy and complicated process. There's a lot of hard math that goes into this. And I've maybe glossed over some of the facts. But I'm trying pretty hard to give you guys a more of an intuition of what's happening here, a more intuitive sense of the things that we're doing. And so I hope you'll forgive me for any possible lapses as a result. I really want to make sure that this is, it's clear that, okay, fine. Okay. So what does a signal really look like? I mean, how do we know when we've seen something? I've shown you that little animation. You got a sense of the fact that we can record things at the end, that they leave energy in weird ways. So let's look at something that's a little bit cleaner. This is what we call an event display. So after we've decided to record the data, and after some very sophisticated algorithms have done a job of reconstructing the objects that that were produced in this collision, we can look at an event and say, there were a couple of, I'm going to teach you how to read an event display so you can do this at the next party you're at. It's a cool party trick. So we look here in the inner detector region, and we see that we have reconstructed tracks, which means we've seen charged particles, electrons or protons, things like that, that are traveling through our detector. Of these, it turns out 2 of those particles deposited energy in those slabs in the calorimeters. And we can measure this energy, and we can measure, based on the information in this inner region, also, again, we can come up with the information about how those particles were traveling, how much energy they had, things like that. And we can look all the way in the center, and we can see that maybe these 2 came from the same point. We're actually able to measure things to incredible accuracies, micron-level accuracies. We can tell that 2 things that were produced, 30 microns apart and just, a couple microns apart, we can tell the ones that were right next to each other, a couple micrometers apart. And so we can take the information from these 2 particles and we can reconstruct the fact that they themselves were the decay of another particle. In this case, what's called a J psi. So these are electrons. You're looking at what we see when we see electrons. This J psi has a mass of 3.17 GeV. Okay, that's great. It's totally compatible with what we know of the J psi. But we do millions of experiments per second. This is, there's no way you're going to look at this figure for each one. So we use a lot of tools, a lot of computer tools to do this. Droves of physicists come up with new ways to cut out things without having to look at it. And eventually we get to smaller data sample. This is my little representation of the fact that we can possibly go hunting through all of this. So say we want to look for something new. Say we wanted to look for a Z boson and hadn't seen it yet. We would do all of these things. We would reconstruct all of these, say, pairs of electrons that look like they came from a common object. We would measure its mass, and we would fill what we call a histogram. So we'd measure one over here at 130-something GeV, and we'd make a mark. And we'd mark all the others that we read, and we'd build up this plot. And as it builds up, something becomes pretty apparent. There's this fall off of stuff that we kind of consider uninteresting. And then, right here, there's a hump. And that is indicative of something new. You've just found a Z boson. So that's the broad idea of how we do searches. Now, we have very complicated ways of doing this. We use multivariate technique, machine learning, neural, okay, who cares? The point, what it really comes down to at the end of the day is the fact that we are looking for something that has a signature that we can pull out from this noise of events that are being produced. That plot I showed you of the J psi, unfortunately we don't see anything like that. Currently, things look a little bit more like this. It's bad. So I told you that these bunches of protons travel the ring 11,000 times per second. There are 1,380 such bunches of millions of protons, right? So bunches of millions of protons coming around the ring, 1,380 of them. That means that you are crossing bunches 15,180,000 times per second. Because there are so many protons and they're so densely packed now, you get 20 collisions per crossing. And that's basically what you're seeing here. Each one of these little points over here represents an actual interaction. But this one with the yellow lines coming out of it, that's the one we're interested in. So we've been developing tools to figure out how to get this stuff. All of these, millions of interactions, we actually have to throw out 99.9% of them. 99.9% are not interesting to us anymore. It's not like we're throwing away things that we care about. Sometimes we do. But the point is to try to go from these 15 million interactions per second in several stages to something like 500 per second. So we have what we call a trigger system. This is actually, I would spend a lot more time on this because it's what I work on, but I think I would bore you. So let me just briefly tell you about it. We would go in several stages from 15 million interactions per second to 65,000 interactions per second. We have to make decisions amazingly quickly. And this is done with some very dedicated hardware. Then from this, we would go to about 7,500 interactions per second. Decisions still have to be made very quickly. We have to decide, is this an interesting event, yay or nay? And we have kind of rudimentary software that can do this for us very quickly as well. And finally, we can then write out these events to tapes. And then we can do the very slow, complicated process of reconstructing things accurately with our more sophisticated software. So we go from these 15 million events per second to 500 per second. Great, fine. The thing is, we expect a Higgs to be produced in 1 out of every 10 billion interactions. So even at these 15 million interactions per second, we're still not producing a whole lot of these guys. They are very difficult to get to. And of these, a lot of them actually we can't detect because they decay in ways that we're not able to pull out of the background. They get thrown out with 99.9% of those events. So I say this is like drinking from a fire hose, and I think that's a pretty good analogy. 500 interactions per second that we then write out. We write out these events. We call them events. We write them to tape. That's actually a lot of data. Every event is somewhere between 1 to 1.5 megabytes. So we're recording 40 gigabytes of data per minute. Netflix is a great example here, because Netflix is routinely mentioned as the largest consumer of bandwidth in North America. It uses up 32.7% of our internet. Right? It's huge. This is a behemoth. It has 24 million subscribers thereabouts, and their total data set size is about 12 terabytes. All of those movies that they're streaming to you. Right? At 40 gigabytes of data per minute, which, by the way, we don't just play in North America, right? I showed you the maps. We play in the US, Europe, Asia, Africa, Australia. We're global, yeah? Our total data set size, 20,000 terabytes. 12. 20,000 terabytes. 12. Yeah, I mean, there are a lot of back episodes you want to maybe throw onto the Netflix catalog, but I don't think they're going to catch up. So when I try to convey to you that we have to throw away all this data, even throwing away all that data, we're still left with a huge amount of information. And so the parsing of that information is very sophisticated. To find that Higgs is, it's not a needle in a haystack. We don't have an analogy for this. It doesn't exist yet. All right. So I'm going to show you a little video now. And what it is it's the code that we use to do this triggering. Yeah? The software that we have. It's a collaborative effort, just like everything else that we do. And so what I'm going to show you represents the structure of our code library and people interacting with that code. So making commits, sending their changes to the servers. So this starts off in 2002 when the trigger was first developed. See, there's this initial bloom of activity as people, and then there's this kind of a structure kind of develops. Each of these things represents a directory structure, and then you have some code, headers and libraries and text files and C code and Python and all sorts of stuff. And you can see that we're all busy little ants zooming across. People are not just sitting on their little piece of code. They interact, they talk to each other. They work on projects with each other. So now I'm going to zoom forward to right before the LHC started producing collisions, 2009. It's humongous. It's huge. And it's still growing. But you can still see we're tiny, so these little flashes of light is us interacting with the code. And we're still zooming across, working across several branches. So even as the collaborations have grown, and even as the complexity has grown, we've continued to be co-workers. I should point out this is still just 1/20th of the collaboration. The trigger is a small part of those 3,000 people, although I would claim a very important one. So anyway, but personally, this is one of the things I love the most about working in the trigger. Is it's a difficult place to be working. It's a do or die kind of a place. If you don't do your job, you can lose data, and that's a couple $1 million down the drain. But there's this huge support group of people all working together. OK, let's get to the point. Now, so I live right near CERN. I eat, my lunch is there. I have tons of friends there. I work on Atlas. I have friends who work on CMS. I can't begin to describe to you the level of excitement that was going on there before July 4th. I mean, the announcement was made, several weeks in advance. The process for getting any result out of Atlas is one where things bubble up from small working groups, and they go through the entire collaboration, and 3,000 names go out on the document that announces a result, and we all nominally have put our stamp of approval on there. So anyone on Atlas is actually able to go and look at any of the results in Atlas as they're being developed. But other than that, it's confidential. So coming up to this announcement, I knew what Atlas had. I didn't know what CMS had. I knew friends on CMS who knew what CMS had. They didn't know what Atlas had. And we were actually amazingly tight-lipped about the whole thing. People really kind of stuck to the embargo. So going in there, even the people who were most in the know only had half the story. It was like Woodstock for physics. It's such an overused Woodstock of, but it really, people slept overnight outside of the auditorium to try to get a seat the next day. This is the auditorium. You see, it hosts a couple hundred people. Each of the experiments is 3,000 people. Not everyone was getting in, and we can do that math. I hear lines in the lobby. It's ridiculous. You'll notice most of the people here are fairly young. They're the ones who didn't have families or who need sleep quite as much as the rest of us. You'll notice that the front rows, the demographics have changed. They're actually skewed more to the older side. These are the people who didn't have to wait. They were a little bit more important than that. So packed room. We were streaming it to various other places on site. I myself was in the Atlas control room because even though we knew this was going on, we still had work to do. So we streamed it to the control room so that those of us there could see the event live. So, is there a Higgs? Remember, I taught you now how to look for signal, right? I showed you how to look for a bump in a plot. What do you think? So, you guys just gave me chills. So yes, there's a Higgs or something like it. Yeah. So you can clearly. Look. I have to say, CMS does a much better job of doctoring their plots. It's so clear over there. Ours is a little bit messier, but we do these very rigorous statistical tests to understand if what we see is sort of just a statistical fluctuation, because this is all probabilities that we're dealing with, and we don't always have a clear understanding of the events. We have all sorts of uncertainties. But we can make statistical statements about how strong we believe something is real signal. And this passes the magical 5 sigma threshold, which means that you're 99.9999 something % sure that it is not fake. So yes. And we can see what a Higgs looks like now, because you also know how to look at event displays. This one's cool, it's 3D and everything. Again, the PR guys had a field day with this stuff. This shows you a Higgs to 2 photons, right? We talked about the photons before. The Higgs can decay to 2 photons. And here they are. These are these red blocks up here. The event is still messy, but we can pick up something here. Now, because this is a messy signature, right? You can see this little bump sits on top of a lot of extra stuff. When we look at this, we can say, oh yeah, this is probably a Higgs. We can't say for sure, but we can measure the parameters of this two-body thing, yeah? And we can estimate its mass and make that plot. The Higgs decays in many different ways, not just to photons. It can also decay to those Z bosons I talked about. Those themselves can decay to electrons and to muons. See, I told you I was giving you the tools you needed. So this, we're much more confident is a Higgs event, because the signature is so clean and so distinctive. When the Higgs decays to two Z's, and that Z decays to a pair of muons, that's this line over here and this line over here, and a pair of electrons, that's this black line over here and this black line over here, we can reconstruct the two different Z's, we can get their masses, and then we can combine those and get the Higgs mass. So here you are quite probably, I'm not going to make a definitive statement because, like I said, there are all sorts of uncertainties, but I can make a statement about the probability that you're seeing a Higgs here, and the probability is quite high. This is what a Higgs looks like. Well, people were pretty excited. So while this was happening at CERN, there was an international conference on particle physics happening in Melbourne, which it was streamed there as well. And so 800 people in this auditorium were clapping at the same time in Australia and over here at CERN. So it's pretty cool. If you happen to wonder how this picture came out, Katie is sitting right there, and she'll be happy to answer your questions after the talk.
It's lovely. It's really good.
OK, why did I say something like it? I gave you maybe a couple hints when I said that there's still some uncertainties in there, right? We're making probabilistic statements. So right now, I mean, we think it quacks like a duck. We think it walks like a duck. But as it turns out, there's still a chance that it could be something completely different. And that's honestly is what we're hoping for. This is a historical event, right? But if this is new physics, even beyond the standard model stuff, if this allows us to peer into new sectors, this opens up a whole new understanding of how the world works. And that's super exciting. There's a huge amount of potential there right now. And why do we feel that there should be something else? Well, we know that there's still plenty to be understood about the Higgs. We only know some, we need more data. The more data we have, the more precisely we'll know it. But we know that the universe remains a fundamentally weird place. We don't fully understand it. There's dark energy and dark matter. Neutrinos have mass. There's all sorts of weird stuff going on there. And so we have these other theories that we're kind of chomping at the bit to understand if they're the true understanding of nature, if they get you closer. We know of ideas like supersymmetry and string theory, and we'd love to get there, and this is maybe a way we do it. So I'd like to thank you for your attention, and I hope that you can now explain the Higgs to all of your friends.
Well, thank you very much. We'll now have some time for questions. So I know that there are people in various locations around here. I'm going to take questions from inside the Panofsky Auditorium. Please wait until you get the microphone so other people can hear the question. We'll have, 15 minutes of questions in here, and then we can break up. But there are numerous experts on this in the audience. They're wearing these funny red hats. Katie, hold up the hat. So we'll be glad to answer privately any questions that you have. But first, let's just take some questions from the audience here. So please, sir.
I heard there were
Oh, could you get him a microphone, please?
too many
Or can you get them?
Take the microphone.
photon pairs.
Take the microphone, please.
I heard that there were too many photon pairs produced more than expected.
Yes. So
Maybe you
still, yeah, okay, I'm still live. I'll repeat the question, yeah. So, so the question was, were there too many photon pairs? Am I still live? Okay, all right. So the question was, are there too many photon pairs produced? Is there new physics? Well, the thing is that we still have to figure that out. it doesn't look like there's that much more than expectation. So when I said that there's these probabilistic statements we make, yeah, right now it's within our bands of uncertainty. We believe it's still totally compatible with a standard model. But it does leave some wiggle room. And it's not just in those photon pairs. We actually see some effects elsewhere in some of the other decays that we need more data to really figure out. But it's got a bunch of us, placing bets.
So, sir,
Has the spin of the hopeful Higgs boson been determined? And if so, to what level of accuracy?
Up until the day before we made this announcement, everyone's like, got to find the Higgs, got to find the Higgs. The day after, everyone's like, we have to measure the spin, we have to measure the spin, we have to measure the spin. No, not yet. So different channels give you different ability to get to that. We don't have a whole lot of statistics in the channels that would give you the precision to measure it. You don't need a whole lot. We should be able to make statements by the end of the year. By the end of the data taking year, which actually has been extended to February. So by sometime after February. Sorry? Yeah. But who knows?
Yeah, in quantum mechanics, spin is quantized. Yeah. So it's either 0, 1, 2, 3, etc. 1 actually we know is excluded. There's a theorem by Mr. Yang who discovered parity violation, that if it decays to 2 photons, it can't be 1. So it's 0 or 2 or something weird, but we'll still find out. Yeah. Okay, sir.
So how many different decay methods are there for the Higgs boson, and what are they?
Okay, so starting from where? So we got Higgs to ZZ, Higgs to WW, Higgs to Tau Tau, Higgs to 2 photons, and then you get down into lower masses, but we don't really count those because they don't come into the equation. There are a dozen or so.
It decays into 2 pairs of most fermions?
That's right. So when the Higgs decays, it can decay into 2 bosons, yeah, or to 2 fermions. Now, depending on the mass of the Higgs, it'll decay predominantly to different types of pairings. The fact that it's actually 125 GeV, the fact that that's the mass, is sort of very fortuitous because it means that you have different. So if you think of the ratios in which it might go, it's sort of the crossing of some of these ratios, and so you have more than one way to probe it. Whereas if it was, let's say, if it was this very heavy object, then you'd only have one way to probe it, and it's nice to have different channels giving you information about it. So
a bigger Higgs decays into bigger particles?
yeah, rule of thumb, yes.
Okay, sorry, who's got the microphone now? You do.
How close do you feel that CERN and the Atlas program are to finding what supersymmetry predicts that the fermions have boson pairs and the bosons have fermions?
Sorry, I didn't catch the first part of the question.
How close do you think CERN is to
Oh.
finding supersymmetry, finding that bosons have fermions and fermions have bosons?
Yeah. So Joanne Hewitt, who's actually a theorist here, gave a talk at the Summer Institute that's going on in parallel, where she basically says, this is a question that people ask her all the time, and she put up a figure that shows different energy regimes, and she made a statement that with a 14 TeV LHC, so the energy that we'll have after our upgrade, and 300 inverse femtobarns, which actually I'm not entirely sure how many years of running that'll be. At that point, supersymmetry will be dead or alive, and we'll know. The thing is, okay, I'm an experimentalist, so I'm going to take a jab at some theorists and say there's always ways to come up with a theory that gets you out of this box. But a lot of supersymmetry space has been constrained now. And a lot of the things people were kind of hoping to see immediately have been shown not to exist, essentially. They've been ruled out. But we have a number of students and staff who work on supersymmetry, and the people are still interested. It's still there. This is a little region.
I'm still working.
Yeah, I am.
In ATLAS, how is the trajectory of a particle measured? Is it measured on the wall of the? Is it measured on the wall of ATLAS, or can you actually plot its trajectory?
Yeah. So I sat in on a, the question was how is the particle measured in ATLAS, the trajectory. I sat in, I was fortunate enough to overhear a guided tour that was happening at ATLAS. And this elderly woman asked the tour guide, but how do you get the particles out of the detector afterwards? Which, I really like that image, but it's actually, it's a subtle point. It's not such a silly question. So what happens is, as I mentioned, we have various different detectors, and they each are designed for specific types of measurements. So if you have a charged particle like an electron or a proton, it's going to go through this detector. It's not going to just smash into it and stay there. It's going to pass through, but it's going to interact with the material we have there. And based on the charge that's left there, we can reconstruct its path. There's a magnet that curves its path, and we can calculate from that curvature what its momentum was, right? So the velocity of that particle is something that we know. Depending on what kind of particle it is after that, it may, so say it is a proton, it will then smash, like I said, into these calorimeters. And when it does so, it interacts with the material there. It produces showers of other particles, but it's cascading. It's depositing all of its energy just iteratively into here. And we can measure the energy deposited in each of these cells of these detectors. And we can then use software to reconstruct it. So to answer your question, in multiple places, in multiple ways. And not all at the face.
Sir, in the back.
Thanks. I was curious what kind of scientific evidence is mounting for the proof of the existence of the graviton and the relation to the Higgs?
Yeah, this is something we do not probe at all at ATLAS. I'm sorry. This is a whole other field of experiments, ultra high precision things that you do with laser interferometers, with giant lever arms. The LHC is entirely too messy a place for that kind of measurement.
Sir.
This is kind of a layman question on Higgs boson. I'm kind of taking from the mass splash analogy that you gave, that the higher the mass, the bigger is the splash, right? But when you talk about a Higgs field, the particle that is going into it has no mass.
So, layman's questions are the ones that scare me the most. So it's, I think what I had said is, it is the interactions with that field that give it the mass. So if this field wasn't there, then they would have no, so if you imagine it had some boundary, and it was sitting outside the field, then it would have no mass, and say it's an electron, it'd be going at the speed of light, and then say it entered this boundary, totally imaginary boundary, then all of a sudden it would have mass, it would slow down, a whole lot of radiation would happen, there'd be a lot of things, but essentially that field is everywhere. So the particle is always interacting with that field, so it's not like the mass turns on and off. Does that answer your question? No, so the particles themselves have mass. And the field, so the Higgs boson itself also has mass. Is that what you're trying to get at? Yeah, so it's the interactions with the Higgs field that gives the Higgs particle mass. It's totally, it's a snake eating its own tail, yeah? But no, all of the mass comes from the interactions with that field. All of it comes with, you can imagine it just, it's actually, like it kind of floats through this field, and as it bumps into excitations of this field, that's essentially where it comes up with the mass. So it's trajectory through the field that gives it this, and things that have a more bouncy trajectory in this field have more mass, and things that slip right through it have less mass.
Okay, let's try something else.
Yeah, various people have proposed a dark matter, weakly interacting massive particle with a mass energy of approximately 120 something GeV. If that's what you found, how would you know that it was a Higgs boson rather than an example of a WIMP?
Right. So it's all about, so how do we know it's a Higgs boson and not a WIMP? It's all about measuring it in multiple ways. But we don't expect a WIMP to have been produced in this way.
Actually, Emanuel, can I answer this one? So if it were dark matter fills the universe. It's been there 13.7 billion years. These things, bang, 10 to the minus 20 seconds and they're gone. So it's a totally different thing. It could be there's a dark matter particle at about the same mass, but, and actually we're trying to look for it at LHC, but this particular signature doesn't show it up. But this thing is something that it's created, it lasts for a tiny fraction of a second, it decays to these two photons. You can see the photons, we're just not fast enough to see the particle itself. And that means it can't be dark matter. It can't be something that's been in the universe for billions of years. Sorry.
No, it's a much better answer than I would have given.
Way up there.
Up here?
Hi.
Up top?
Hi.
Over here first.
Oh, yes.
I was just wondering, can you give us an idea of how many Higgs particles you have to observe in order to be able to detect it from background? You know, when you look at the plot, are we seeing just the 1 in 10 billion? Are we seeing multiple? Do they decay in the same way? And what criterion go into that plot?
Right. This is an excellent question. So how many of the particle do we need to record to know that it is that particle and not something else? And it depends entirely on the way in which you are measuring that particle. So in the case of two photons, which is in some sense the favored channel at the LHC, you can see here that this is a bump of, what, 100 or so over 800 or so. So you need, for every 800 background events, you need 100 signal events to make a definitive statement. What I haven't shown you here is that we've got similar plots for the other channels, like so the ZZ channel. The ZZ channel is really amazingly clean. We're talking a handful of events, 7. And that's all you need. So the reason for that is a lot of stuff can produce 2 photons. And not only that, it's produced in abundance. The background is produced at a very large rate. A few things can produce 2 Z bosons. In fact, it's also produced at a pretty substantial rate. But the signature is much more distinctive. And so you don't need as much.
Yeah, I should say also that the probability for a Higgs to decay to 2 photons is a couple parts in 1,000. So you need 1,000 Higgs bosons to get one event on this plot. So it's all in all, it's daunting.
Yeah. That's the.
Okay, let's take 2 more questions and then we'll end the formal
My question
parts.
has
So
to
there's
do
one up
with
there.
the data
No,
sets.
2 questions? You 1 question.
Well, they're co-related. Basically, I understand that the vast majority of all data is just thrown out and gone. Of the data that is retained, the question I ask is, how long will those data sets be retained for perusal?
Yeah.
And then I'll say why I asked that question was that when supernova 1987 went off, they went back and looked through the back data and they found out that the neutrinos had arrived ahead of the.
Yeah. So yeah, right. So the archiving of this data, the long life of this data. So I worked on the Tevatron before working at the LHC. The Tevatron is, well, they've turned off the lights. That is also a huge data set, and there have been some very active discussions about how you retain. It's not just about retaining the data, but the ability to read the data. How do you keep the environment that we use to reconstruct these particles? How do you keep the knowledge? Babar ran here. Similarly, no longer working, closed down a couple years ago. Right now, one way people think of doing things is through virtualization. All right, you can actually just take a snapshot of the software that you're using, and then you can run virtual machines that basically take you back in time and allow you to run this stuff. But even that is dangerous because the data, the actual storage can decay. So you have to copy that data from that. So people are having active discussions about this. The data will be kept. This is valuable data. It will not be thrown out. And more importantly, we are building on past lessons to get there.
Last question. Please.
So this is from a non-particle physicist. One of the things I'm wondering about is, as you measure all of these events, does Heisenberg uncertainty come into play at all? I mean, you're talking about momentum and trajectories in the same sentence, and are you actually altering what you're measuring? And then how can you be sure of what you're measuring? And then when you put this in the larger perspective, is the Higgs boson, this discovery, just fulfilling what you predicted in the standard model, or are you opening up a whole new kind of physics?
Boy, I wish I thought that I could affect reality like that. No, it's okay. Heisenberg, the uncertainty principle is at work everywhere. But it's actually, I mentioned a number of times the uncertainties that we have. They're at much larger scales. Our apparatus is imprecise. It's really precise, but given what we're trying to measure, it's still imprecise. We have 10% level uncertainties, 5% level uncertainties. These are very big on the scale of things. Do we affect stuff by measuring it? Well, yes, in the sense that stuff always works, but it's not, well, it's a deep question to ask. I don't think that we're producing the Higgs just by thinking about it. It could have been a lot cheaper otherwise. No, so it's a different scale is essentially the answer, though.
Okay. Well, I think that's probably a good place to stop. Let's thank Emanuel again.
Thank you.